All right, so section 6.1, we're talking vectors. So we're going to go through three things today. I've got it up on the board here. First of all, we're going to define what a vector is, for those of us that are not familiar with the concept yet. We're going to do what's called resolving a vector, and then we're also going to find the magnitude and direction of a vector. Anybody that's seen Despicable Me remembers the vector, the magnitude, and the direction. We're going to talk about what that actually is today. Okay. All right. So basically, the definition of a vector is pretty straightforward. It is a directed line segment. Period. And what that means is it's a line segment that has a direction to it. Okay. So usually, if you had some sort of line segment that you would graph in the coordinate plane, just might look like something like that. Okay. There's two endpoints to it. Okay. Well, we have talked about in the past with parametrics. There was always a direction to the flow of how it went. So there was a starting point and an ending point, that sort of thing. So if I want to turn this line segment into a directed line segment, there's going to be a flow through it. There's going to be a direction through it that it takes. And so let's say I wanted the direction of this to go that way. Okay. Then my line segment, I'd put an arrow up here. And it looks like a ray. It really looks the same as a ray. But it still holds on to that end point. Okay, it has a starting point and it has an ending point. A ray in geometry, the arrow is just there to indicate that it continues to go on forever, right? It doesn't stop. So if I could keep drawing it with my pencil, I'd just keep going. Okay, with this, it actually stops, but at the same time, it does have a direction to it. It is going up and to the right. It's not going down to the left. It's going up to the right. So it has a start and an end to where it's at. Okay, so we have an initial point and a terminal point for every vector. Okay, so for this one, let's say this first point was at 3, 2, and then the end of it was at 6. Maybe this would be up at 6, I guess. Okay, so the initial point would be at 3, 2, and the terminal point would be at 6, 6, based on the direction that I created for that vector. Okay. Now, vectors can have lots of uses, and we'll get into this mostly tomorrow. We get into more applications of the vectors themselves here, but vectors can represent anything from force, if you're talking, physics again, if you're pushing on something, the force, which then shows you the direction of the force that it's pushing it. It can represent velocity, acceleration, anything that you can measure while something is moving in a particular direction, a vector is useful for. Okay, so usually force, velocity, acceleration, those are the things we're going to be looking at with these. But there are other things too that we can use them for as well. Okay, so usually a vector, when we graph it like this, is going to be what's called standard position. And standard position simply is the initial point is at the origin. That's it. So if we want to figure out some information about our vector, say magnitude and direction or whatever, it just makes the calculations easier. Okay? So if we move the vector, kind of think about picking it up off the page, moving it, and then dropping it back down so that that initial point sits on the origin, then you've moved that vector into standard position. And it makes all that calculation, like I said, a little bit easier to do. Okay? So because of that, though, then we have equivalent vectors. So as long as I can pick a vector up and move it around, okay, I'm not really changing anything about it. I'm just changing technically where it's sitting, but all that calculation stuff that I would do with it remains the same. Okay? Kind of, yeah. Yeah. So we call them equivalent vectors, but congruent vectors might be a more apt term, though. So equivalent vectors are any vectors that have the same, or are basically the same, but the only difference is a translation of some sort. And so I'm going to put in parentheses down here, magnitude and direction remain the same. Okay, and magnitude and direction, that's where we're going to go next here now. Okay, so to calculate the magnitude and direction of a vector, magnitude simply is the length of the vector, okay? And the direction of the vector is the angle that it's going off at, okay? So let's jot that down underneath here too, just so we've got that with this. Okay, so magnitude is the length of the vector. And the direction is the angle of the vector. So if we know the initial and terminal points of a vector, that's enough information where we can do this kind of calculation. Okay? So what we're going to do is we're going to take a vector, we're going to pick it up, move it, put it into standard position, and we're going to do these two calculations. We're going to figure out what is the magnitude and what is the direction of that vector then, after we have that thing in standard position. Because of this equivalent vectors idea, it would be the magnitude and direction of the vector when it started, too. I've just picked it up and moved it and translated it, so I'm not changing those two things. I'm just making it easier for myself to do that. Okay, so let's say we have a vector that starts at A. To 5 and goes to B. Say 3, 8. Okay, and so the notation for the vector, well, I'll just put it right in the question here. So what is the magnitude and direction of, bless you. Now be really careful with this symbol that's on the top here. This is how you tell the difference between an array and a vector. See how that's only half of an arrowhead there? All you do is the top half of the arrowhead, and that makes it a vector, the notation. Okay? That's the notation for a vector. If you were to complete the arrowhead, then it's array. Okay? Yes. I guess that's true. It's all about the details in math class, right? So, notation-wise especially. So, you will.
Anything outside of physics. physics is average.
Depends on if you use physics in your real life.
Again, anything outside of physics, well, if your career takes you a pathway of working with things that exist, then you'll use physics. Not necessarily.
If you want to describe the motion of something that exists to someone else at some point in your life, then you will use this in your life.
You don't have to use vector form.
It makes it simple, though. It really does. Anyway, so we'll draw this out. You don't always have to draw out the vectors. We'll kind of talk about how you can get around having to draw it every single time. But for now, since we're still learning about it, we'll draw this thing out. All right, so 2, 4, 6, 8. Okay. So we start at, and see how here too you can tell which is the initial and which is the terminal point, right? Based on the notation here. The first letter is always the initial, the second letter is always going to be the terminal. So this vector is going to start at 2, 5, which would be here. So there's A. And then it's going to end up at 3, 8. So there's your B. And so this vector is going to start there. And there's its arrowhead. So something kind of like that. All right, so let's start by taking this thing, bless you, and moving it into standard position. Okay, so A is going to translate to the origin now. So if A goes to the origin, where does B have to be? One, 3. Good. How did you know that? Okay. So if A is now at 0, 0, it's all about the difference between them, right? So from 2 to 3, it's a difference of 1. So this new coordinate for B is going to have to be a 1. 5 to 8 is a difference of 3. So that's got to be 3. I always did it by looking at the graph, at least to get started with these. So if you look here, wherever A is, I'm going to have to go over 1 and up 3, right? So if I'm at 0, 0, over 1, up 3. Should hold that same angle, right? That same, think of it like a slope, right? Rise over run. The rise over run should be the same from the initial point to the terminal point. So if that holds true, we should be at 1, 3. Okay. So this vector, I can now put it into what's called component form. If I'm in standard form, this vector AB, and I've used these kind of brackets now. It's the little triangular kind of brackets there. So that's going to be 1, 3. I'm only using the coordinates for B, because the coordinates for B are really the only ones now that I'm going to be worried about. Because the coordinates of A, if I'm in standard position, are always the same, right? It's always 0, 0. So I don't need to concern myself with that anymore. I know that's going to be there. It's just a matter of, okay, where's B? Where's the other part of it? Where's the terminal point of it? And the terminal point in this case is 1, 3. So in component form, I'm just going to... Now I can start to figure out my magnitude and my direction. So let's start with the magnitude. Magnitude is the length of the vector. Okay? Think triangles with this stuff. Exactly. If I make this into a little triangle there, I'll zoom that in just a little bit. It's a little... It'll work. Good enough for now. Well, no. I still dislike it. Okay, so in this little triangle, this is a length of 1, this is a length of 3. How can I find the length of my vector then? Yes? Yeah, Pythagorean theorem will get it done. Okay, so the magnitude you don't need that, but you could. All right, so 1 squared plus 3 squared equals c squared. So that's going to be, what, square root of 10? Yeah. All right, so here's another notation thing for you. Magnitude is a length of, or distance from 0 in this case, because it's in component form. Something else you guys have studied in the past that measures something's distance from 0? Anybody remember? Absolute value, right? So the notation for the magnitude is an absolute value symbol. So for this one, the absolute value of the vector AB equals the square root of 10. So if you see an absolute value symbol like that, it's actually talking about magnitude.
So that this whole time, that's why you've been saying distance from 0 instead of just make it positive.
Right.
Okay.
Yeah.
That actually makes sense after you.
Absolute value really measures the length of things from 0. Yeah. So there's your magnitude. Now direction. How do we measure direction? I guess one way of doing it, though it's not really the accepted way, but one way of doing it, you could try slope. Okay, we're basically trying to figure out how sloped is it. Okay, but the more acceptable way of writing out a direction, which I'm going to have you guys do because it has a lot more utility to it later, is figuring out this angle. You guys all see that little theta I stuck in there? Oops, you can't see it on the other one though. There we go. Okay, we need to figure out theta. How do we figure out that angle? It's a right triangle. You guys have studied a lot of trig at this point. You don't need a law of sines. Yeah? You can do a tangent. You guys all see that? Tangent of theta is equal to what in this triangle? 3 over 1, opposite over adjacent. Inverse tangent of 3. Yep. Okay, now, this is the one place, well, there's a couple others, but usually we do radians. In this case, when we're talking vectors, because it has such a close tie to physics, and in physics, they love their degrees, we're going to do these in degrees. Okay, so put your calculator back into degrees if it's not there right now, and then do the inverse tangent. A little bit. Job harder. Silly, lazy physics people.
Degrees, though, is that we just picked a number?
Yep.
Okay, this number we can divide by a lot of things. Let's use it.
Yep.
It has no significance other than we said it has significance.
Yep. All right, so our direction theta, inverse tangent of 3, should be about 71.56 degrees. Yep, for vectors, for like the next, well, 2 sections, 6.1 and 6.2, we're pretty much going to be exclusively in degrees again. Yeah, sorry. Anytime we deal with vectors, we're talking degrees, just because of that physics stuff. So, this particular vector had a length of the square root of 10, so about 3.2 or something, and its direction was 71.56 degrees. So direction is always off the positive x-axis, and the length is always, well, the length. Okay. Now each of these, there was a little process that we took that we will continue to do over and over and over and over and over again. So if you want the magnitude and direction of a vector, we've got these little formulas we can plug into. So we're going to jot those down next just so we have them. Yeah. The length of it being negative, or a vector that goes into like an... Yes. And we're going to look at that in a second.
Or do you have to put something like 6 degrees above the horizon line for this one?
We're going to just make them positive and negative angles rather than above and below the horizon. But for in physics, yeah, you guys do it that way instead. So, okay. So I'm going to back this up again. I might have to refocus, but I need more space. Darn this thing. Okay. So, magnitude. Okay, so we're going to, for all of these, we're going to just talk about, we're going to call the vector just vector v. Okay? You don't have to use 2 letters like we did with the last one. Sometimes they just call it a letter. And so for the magnitude, vector v would look like that. Okay, the length of vector v. You always do the square root of x squared plus y squared. See how that's really just the Pythagorean theorem kind of stuck in there? Okay? The magnitude was the c part of the Pythagorean theorem. So if you solve the Pythagorean theorem for c equals the square root of a squared plus b squared. But what's a and b really in this picture? It's x and y, right? So it's the square root of x squared plus y squared. That's what we were doing. And the direction, which we call theta, we did the inverse tangent. Now go back and take a look at the last example. Was it x over y or y over x? Which way did we do it? Y over x. Yeah. So inverse tangent y over x. So now, you don't have to worry about graphing it. You don't have to worry about trying to plug things in the right way. You can just take these 2 formulas, and if I give you a vector in component form, stick it in. Okay? So, give you an example. Okay, so let's try this out. See if you guys can do it. I'm going to give you a vector, already putting it in component form for you. Or I'm sorry, yeah, it is component form. So it's already in standard position then, okay? And I would like you to take these 2 formulas, tell me the magnitude and direction of this vector. I'm calling it W. Yes, sir. Did I do the same numbers? Hold on a second. Don't want to do that. There. He wants to get more out of his learning, so that's fine. So, direction of -1, -5. A little bit more interesting. All right, everybody got answers for those two? Need more time? No more time. Okay. I'm going to show you what I got. See how it compares. One of these two answers is wrong. You tell me which one is wrong. How do you figure it out? Yeah? What's supposed to be negative? Magnitude will always be positive because magnitude's a length, right? So actually, that one's okay. Something's wrong with the angle. Now, if you guys just type this into your calculators, just the way I did, everything's fine, right? Should have gotten 78.69. But what's wrong with 78.69? Look at the vector I started you with. Goes down, not up, right? Here's the problem with that inverse tangent little formula that we're using. It's good most of the time. Most of the time. Sometimes it gives you a wrong answer, though. Negative 5 divided by negative 1. What is that? 5. So if I had given you the vector 1, 5, wouldn't it give you the exact same answer? And one of those vectors is going up and the other vector is going down. It's not the same direction. Okay? It's 180 degrees off. Exactly. Okay? So, because this vector, and I'm going to draw a quick little sketch of it over here, it goes negative 1, negative 5, so it's doing something kind of like this-ish. Pretend like it's straight. It's doing something kind of like that. So, if I had 78.69 degrees, 90 degrees is just to here, right? So this angle is only taking us to here. There's your 78.69. So do you see how I'm off by 180 degrees there? I have to rotate it to be, okay? So, if this happens, you need to add 180 degrees to it. So it's actually 78.69 plus 180. It's actually 258.69 degrees. So there's your direction. Okay? And again, it's always off of the positive x-axis. 8.69. That's fine. That's this angle all the way to there. That's the one you want. Okay? Now, the nice thing is, you can know ahead of time if your inverse tangent on your calculator is going to give you a wrong answer or not. Okay? There are certain quadrants where we have problems. First quadrant. Is first quadrant going to be a problem? Ended up in the third quadrant. Third quadrant is a problem. Okay? And then we still have 2 and 4. Okay? One of those works out okay, and one of those presents a problem again. In your calculator, when you do inverse tangent, you guys remember we talked about inverse tangent, what quadrants in the unit circle it's defined for? 1 and 4. So your calculator is assuming one of those two. So if your vector is in 2, I'm going to give you a wrong answer. Okay? So quadrants 2 and 3, you have to adjust it so that it's correct. And that means adding 180 degrees to it. We could. But if you just remember that rule, it's easier. But because the formula we would use would have to say, if your x and y are within this range, then do this. If not, do that, which is really just kind of what you're remembering by what quadrant it's in anyway. So, anywho, so here's the thing. So this inverse tangent of y over x. So if your vector is in quadrant 2 or quadrant 3, add 180 degrees to it. and then you'll be fine. Yes. I'll show you. If your x is negative, yeah, essentially. Okay.
Wait, wouldn't you subtract 180 because it would give you an answer in quadrant 4?
That's what I was just about to address. Whoops, if x is negative. All right, so let's try this quadrant 2-4 thing, and I'll show you. So let's say we've got the vector v equals, if I want to put it in quadrant 4, x needs to be positive. Oh, wait.
No, I was saying if your vector is in quadrant 2.
No, 2, right.
It gives you an answer that's in quadrant 4. So
Right.
you need to subtract 180.
Yeah, no, I was just in the wrong place. So negative 2, positive 7, let's say. It's going to give you a negative answer. Okay. Inverse tangent will give you a negative answer. You add 180, you're still good. Okay, so let's just do it real quick. Okay, so if this is my vector, negative 2, 7, quadrant 2, one of the problem quadrants, right? So if I'm going to find the direction of this, I'm going to do the inverse tangent of 7 over negative 2, which my calculator tells me is negative 74.05 degrees, which I know is wrong because negative 74.05 degrees is in the fourth quadrant, just rotated down negative. And so if I add 180 to that, I have 105.95 degrees, which is in the second quadrant, which is what I want. Okay. Adding those? No. I used the calculator, so no. Anyway, so basically, if x is negative, or if you just think about what quadrant is this in, is it in 2 or 3, then I need to do this. But, yeah. So just be careful with that. Otherwise, you can plug them in the formulas and you can feel safe about it. Okay. If I was using radians instead of degrees, you would have to add pi, right? Mm-hmm. But you're not going to typically see radians with vectors, so yeah. Okay. Next thing we want to talk about is going the. What if you know the magnitude and direction of your vector, and you want it back in component form? Because there are things where we want it in component form to do, which we'll talk about tomorrow, like adding vectors together and some other stuff. So we need to resolve the vector. Okay, so let's say the magnitude of vector m is 8, and the angle of vector m is 25 degrees. And I want to know what's the component form. So what is the component form of vector m? Well, to help you with this, let me draw you a picture real quick here. We're going to see if we can do a little trigonometry here again with some triangles to help us. So here's in standard position again, right? Because I want it in component form. The length of the vector is 8, so it's coming up like this. It's got a length of 8. And the angle at which it's coming up at is 25 degrees. Okay, so here's our vector m. The component form is x and y. Right? Basically, I want to know what are the coordinates of the little point where the arrowhead is. So I'm going to just draw this like a right triangle, and I want to see if you guys can tell me what I need to do. I need to find the coordinates of where this little arrowhead is up here. You could do law signs, but we don't need to. Do what? Sine and cosine. Here's x, here's y, right? Oh, yeah, don't do that. So, how could I use sine and cosine then to help me? Yeah.
So if you set it up as like sine of 25 equals y over 8, and then you can just multiply the 8 to the other side.
Mm-hmm. Yeah, yeah. So y equals 8 times the sine of 25. And then what about x? What can I do with that? You could. It's true. Otherwise, you can do the cosine. So x equals 8 times the cosine of 25. Take a look at what I started with. The magnitude was 8, the angle is 25 degrees. X is 8 cosine of 25, y is 8 sine of 25. See a little pattern we can keep using here? See how there's like little formulas we could just keep applying every single time?
So you could just do like the hypotenuse times sine of angle.
X is magnitude times the cosine of the direction, and y is the magnitude times the sine of the direction. Every time. That works. And there's no little tricky inverse tangent, oh, sometimes it doesn't work. This always works, no matter what. It'll always give you the right answer. So, let's actually figure these out, though. So, what is 8 sine of 25? Oops. 3.38, yep. And the 8 cosine of 25 is 7.25. All right, so this vector m in component form, let's see, the x always comes first. So 7.25, comma, 3.38. That would be your answer then. All right, so in general, though, and I'm going to go back to my vector v. Okay, in general, that's going to be what you're doing. The first component, the x component, is always magnitude cosine of the direction. The y component, the second component, magnitude of the vector times the sine of the direction. All right, I'm going to let you guys practice this just a little bit here, okay? Give you a couple of vector situations where I give you the magnitude and direction, and you tell me what the component form is for each, okay? All right, so the first one, the magnitude is the square root of 20, and the direction is 135 degrees. And the next one, let's make this the vector c. Say its magnitude is 7. And its direction is 90 degrees. And this one, I want no calculator. You got it. You can do it. In fact, the first one, You could do the first one without a calculator too, but I'm going to be nice. But second one, no calculator. Do it by hand.
So, I have a question.
Yeah.
Is there any little issues when going backwards?
No, there's not. Nope. Inverse tangent is works real nice. Yeah, no calculator on that one. It's 90 degrees. You can do it. Let's say 2 decimal places. You could. Your answer would have square roots in it. But yeah.
The first one is the X and Y plus the
Yep.
Okay.
Mm-hmm. All right, anybody more time? We got a few people. Okay. Okay, so the first one, x would be square root of 20 times the cosine of 135. So negative 3.16. And the y would be the square root of 20 sine of be positive, yeah. Right, yeah. I was hoping you guys would recognize that. If you got theta of 135 degrees, that's putting you in the second quadrant, okay? So this is kind of a way to check your work a little bit, at least as far as the positive negative stuff goes. You know in the second quadrant x is negative and y is positive, right? So you got to double check your answer. Am I getting a negative x and a positive y? Yep. And 135 we know is that halfway point in the second quadrant. So they should have the same value except one's positive, one's negative, and that's it, okay? So our component form for b would be negative 3.16, 3.16. Okay, if that was really mean, that would make you do that one without a calculator either, and then there'd be a bunch of square root business you'd have to multiply, but I'll be nice. Now, this one, you don't even really need the formulas for the second one. Where's it pointing? Straight up. What's its magnitude? 7. What are the coordinates? 0, positive 7, right? If it's pointing straight up, x is 0, y is 7. Done. 0, 7. use the formulas, go for it. It'll still work. Quickly, it really makes it easy. 90 degrees is straight up. So if I give you an angle that's... If it was an angle that is quadrantal, which means right on an axis, like 90, 180, it's called quadrantal. Yeah. So 90, 180, 270, 360, one of those, just think about what the graph looks like, and it's way easier. But if you want to be safe, plug it in the formula, see if you get the same thing. But, yeah. So this should have been the 2 that you had for that. All right, so for the remainder of the day today and into tomorrow, vectors in component form, like this. And I'm going to ask you to do something to the vector based on what it looks like in the graph, and we're going to see what we need to do then to these to make that happen. Okay? So I'll give you an example. Let's say I got a vector and I want to make it twice as long. Okay? So I've got, let's say I got the vector n, and it is 3, -5. So what is the component form for the vector twice as long as n, same direction? Just hold that thought. Okay, so I'm going to do it the long way, but then we'll come back to what you're talking about. I'm proving it to you. I'm proving it to you, okay? All right, so if I'm going to make a vector twice as long as n, first of all, I need to figure out what's the magnitude of n and then double that, okay? So let's find the magnitude of n. So the square root of 3 squared plus -5 squared. So that gives us, what do we got exactly here? Square root of 30. Okay, yeah. Yeah, well. Okay, so that's the magnitude. So our new magnitude would be 2 times the square root of 34, correct? If we're going to make it twice as long, it has to have twice the magnitude. So just take that and double it. Okay. I want to have it in the same direction. So I got to figure out the direction of this one. This right here? If you want to do that, sure. Y over x, -5 over 3. Okay. So the inverse tangent of -5 over 3... My calculator's telling me -59 degrees. Now, negative?
Yeah.
That's fourth quadrant. We're good. Okay. I was. I'm going to go... Please do the inverse tangent of negative. No. Okay. So I need to figure out a vector that has the magnitude 2 square root 34 and has a direction of -59.04. Okay? So we just talked about that, right? If we know a magnitude and we know a direction, we can plug it into that sine and cosine, those two formulas. So our x is going to be 2 square root of 34 times the cosine of -59.04. And the y is going to be 2 square root 34 times the sine of -59.04.
Yeah, like say you make an effort to save a copy, but it dies anyways, that's not an A.
for the effort, not for the outcome.
Oh, no, it's grading your effort.
Not the outcome.
Whether you tried, not whether you succeeded.
Yeah,
Okay, shh. I'm getting off topic. Okay. Yeah. All right. Shh. So here's what I ended up with. My new components are 6 and negative 10. If your name is not Josh, what do you notice?
You just doubled it.
You just doubled the original ones, right?
it's going to do that anyway.
Hooray!
Right.
No, it's right. So that's just proving it to you, though. Okay. If you want to make a vector twice as long, guess what? You just multiply the components by 2. Okay. Or if you want to make a vector 6 times as long, you can multiply the components by 6. Okay.
I really hope there's somebody out there listening to all your lectures on YouTube just for our class little comment. And they can't see you, and they're like, what?
What is going on in that class? Learning's happening, I swear. So, take the shortcut, okay? So, if I'm running out of is negative 2, 7.
I hope that was fancy because of that. He does yours, he does it for you during your hour. No, I hope he's just like oh, no.
You're a double side job. I'm
It's blurry.
Whoa, what just happened?
You broke it.
Darn it. Today?
How do you do that?
Just keep zooming in and out.
Yeah.
Continue.
Keep it in motion.
Some.
Fine.
Wait. Oh, there we go.
Oh, it's up.
Look at that.
Okay, so what is the component form for the vector 1/4 the length of p in the same direction?
1/2 and 1/4. No, it's negative 1/2. Ooh. Negative 1/2. I wrote the negative. Negative 1/2. And 1/4.
So, yeah, so you're going to multiply everything by 1/4. So think of it this way. It's like doing 1/4 times negative 2, 7, and you're distributing, right? Just multiply that in. So you end up with negative 1/2 and 4ths.
1 and 3/4.
Or 1 3/4. Yeah, right. Hey, improper fractions have their place.
Not in the real world.
Okay. All right. One last question for you for today. And let's see if you can do it. I'm going to take this idea and I'm going to make it a little different. Let's use Q. So let's say vector Q is 8, negative 2, and I would like you to find the component form of a vector that is in.
I wrote it in the
Hey, I'm in the middle of talking. So I would like you to come up with a component form of a vector, direction as Q, but its length is 1. I'll write it out in case you forget.
Wait, what do you mean by length?
The magnitude has to be 1.
No.
So it's basically that. What is the component form for the vector with magnitude equal to 1 in the same direction as Q? Correct. Angle stays the same, magnitude changes. Yeah.
So what if we take the magnitude of that and then
You divide everything by the square root.
You're right. You have to do something with the magnitude of
I
that.
don't know how to word it. I know what I mean.
Well, we'll do it then. If you can you actually do it without saying it? No? Oh. Keep thinking. Yeah.
You take the magnitude and divide it by yourself. And then divide everything that to be parallel.
Yep. Yep. Got it.
Oh!
Not quite 1, not quite negative 4.
Yes?
0.97 is negative 0.24.
You had a thought though?
I had a thought.
Do it, right?
Oh. There's actually two different ways you could do this one. I've heard one person say one way. I haven't heard the other one yet though.
I feel like the way that you said was easier.
It is.
Well, why does it matter that there's another way to do it if it's...
Oh, expand your mind, Willa.
Seriously, though. I mean, too much is...
It depends on the situation which way you'd want to do it.
For example... Yeah, give us an example where there's a different way that's...
Well, I don't want to give away both methods for doing it right now because I want you guys to think about those on your own.
We're not gonna, though.
Yes, you are.
You keep thinking...
One person already came up with one. I'm sure more people can come up with the other.
We don't need to come up with it. We know the easy way to do it.
How do you know if the other way is easier?
He said it was.
The problem with that kind of line of thinking is that you start to think about this stuff as tricks. Oh, but there's this trick I can do to get to the answer, and it works.
It's just the simplest way to do it. Yeah.
But I'm saying, but then you start to lose the conceptual understanding of what it is you're actually doing, while doing it the more quote unquote difficult way. Conceptually ties things into other things you've learned a little bit better, so it helps you to remember it better. While it takes more time, it relates to things better, though.
We just do it the easy way.
If you keep doing things the easy way, that's fine, but you're going to have to memorize a whole bunch of little formulas in your head and not connect any of them together. If that's the way you like to learn, go for it. But, I'm just saying, there's value the other way. Okay, so, here's the thing. One way to do it, which I heard someone say, was if you take the magnitude of this and then divide both of the components by that, that should work. Because the magnitude divided by itself is what? 1. So if you want to bring that magnitude down to 1, divide it by itself. So figure out the magnitude and divide both of them. The other way to think about it is to do the sine and cosine. What you need to do is, first of all, you need to figure out what's the angle, what's the direction. Shh. I keep the same direction, right? All right, so let's do the direction of this thing real quick. Inverse tangent of negative 2 over 8 is negative 14.03. That's going to put us in the fourth quadrant, which is what we want. Magnitude to be 1, correct? This works then? Magnitude is 1, angle is the same. I don't think it's more complicated. I'm keeping the magnitude what I want it to be, 1. And I'm same as what I got for Q, negative 14.04. If I plug both those in, I should get the components that way. Okay, now dividing by the magnitude, that's fine. That works too. In fact, I think the equation in your book for this even tells you to do it that way. But this is totally valid as well. So your x, you get 0.97, and your y, let's see, sine of negative 14.036. So I'm getting that 0.97 and negative 0.24. Did we all get that as an answer? Those of us that have done it. What you guys just did right there was calculate what's called a unit vector. Why do you suppose it's called a unit vector? It is one unit. Just like the unit circle has a radius of 1, right? That is not a coincidence. Okay, we're going to stop for today. We will do some more calculations with vectors tomorrow. We actually got through quite a bit today, so we don't have a ton to do tomorrow. And okay, so adding and subtracting vectors. If you have two vectors that are in component form, it's pretty straightforward. So let's say I have vector v, and I'm going to define vector v as 2, -1. And we'll do vector w is -3, 7. And let's say I want to add vector v to vector w. Well, all I got to do is add up the components. Or it's kind of like adding like terms. You add the x to the x, you add the y to the y, done. It really is that easy. Okay. Well, because it leads to some other stuff later. So, all right. So, what is v plus w then? Do the addition for me. -1, 6. Yep, you're just adding the components together. And then, hey, let's say I want to subtract these two instead. Then what would it be? Careful. Almost. What's 2 minus -3? 5. Positive 5. And then -1 minus 7. -8. All right. So you guys think you're pretty good at this, huh? No, you're supposed to say yes.
You got to throw it, right?
What if I want 3v plus 2w? Right? Yeah. So 3v would be 6, -3. And 2w would be -6, 14. And then, yeah, then add up their components. So what do we have? Or, nope, 0, 11. Yeah. Okay, so you can do like little combinations like that too. Okay, so if you multiply the vector by something and then add them together, you can do that too. Okay. All right. So I think you get that basic gist there. We're going to use this again, like I said, when we do the story problem stuff, so kind of file that away for a minute. Real quick, want to do some vector equation stuff. This, I probably don't even need to show it to you, but you guys could just reason it out. But figured, And we'll just do this. We'll start with an easy one. Welcome to your first vector equation. A vector equal to a vector, and there's going to be little variables like sprinkled around in there. Okay? So, if 2a3 needs to equal 4,3, what do you suppose a has to be? Yeah, right? Okay, good. That one was sneaky. Okay. Okay, the next one. How about if I have b minus 4, make that a 5. What about something like that then? B minus 4, 5 equals 3x plus 8, 2. How do you suppose you'd approach something like that? So actually add the second set there? Is that what you're saying? Okay. So then we'd have b minus 4, 5 equals, what's 3 plus 8? 11. And then x plus 2. Okay. So, can we do this now? Okay. Perfect. So b minus 4 equals 11, and 5 is equal to x plus 2. Okay, so what's the value of b then? 15, good. And the value of x? 3, yeah. Good, okay. Feeling comfortable with vector equations? Good, we're moving on. I didn't figure I needed to spend a lot of time with that sort of thing. That's pretty much it, as far as what I want you to do with it right now. Nope, no multiplying or dividing just yet, because multiplying and dividing vectors is this whole other can of worms that we're not going to get into right now. But we will when we talk about the dot product tomorrow. So, for now, we're going to leave it be. Okay? Okay, so some story problem stuff. I think I'm probably just going to do one of them with you and call it good. All right, so I said vectors can represent lots of different things, right? They can be force, they can be velocity, they can be acceleration, all sorts of different things. We're going to deal with velocity here for a minute, and we're going to look at a situation where we have two things that are moving, interacting with one another. We have an airplane that's flying. Okay, so it's got its own vector, and then we're going to have a gust of wind that comes and pushes the plane as it's moving, and we want to figure out what is the plane's final speed and direction. Okay, so the plane's going to have a speed and direction, the gust of wind is going to have a speed and direction, and then what is the result of that? Okay, so physically what's going on there is you're adding the two vectors together, right? You get the two vectors working together to create a new vector. Okay? No, it's totally correct. We're assuming that that's all been taken into account already. We're not going to get that nitty-gritty with it. Okay, so if you know after wind resistance and whatever other physics crap you want to throw in there, the plane has a certain magnitude and direction to it, or speed and direction, and then the wind has its own speed and direction. And when those two come together, adding those two vectors together is where that plane is ultimately going to go then. Okay, so... And I'm going to give you the information here in the way that a physics teacher might do it too, just so we're kind of comfortable with that type of way of doing it. So let's say we have a plane. Is flying 25 degrees west of north. We'll explain this in a minute. At a speed of 250 miles per hour. Okay, a gust of wind at, let's say, 10 degrees south of west hits the plane at 40 miles per hour. So the question is, what is the resultant speed and direction of the plane? Okay, so let me zoom this in just a little bit and try and clean it up. This camera's been a little wonky lately. Maybe we could do better than that. There you go, that's better. Okay, so what we need to do here is, if we're going to add the two vectors, one for the plane, one for the wind, we have to actually come up with what those vectors are, right? Put them in component form. and see what we have so that we can do our simple addition with the two of them once we got it. So, let's start with the plane. Alright, we said the plane is flying at 25 degrees west of north. Has anybody ever heard of something described that way before? A couple of you guys? Okay. Alright, so here's what it looks like. Just think of the coordinate plane as being like the compass rose. Okay, so you've got north, east, south, and west. Okay, if you are 25 degrees west of north, that means you start at north and you move towards west, which means you would be going this way. Okay, 25 degrees off of north, that way. Okay, so 25 degrees west of north will be tilting down like this. If you had 25 degrees east of north, then it would come down like this. Okay, does that make sense of where to get that angle then? Because here's the thing. If I'm going to do that, okay, that means this is 25 degrees. The angle I want to use for my vector, though, is always off of the positive x-axis. That's how we've always measured angles on the coordinate plane, right? So in this case, it should be off of east. So if it's 25 degrees west of north, what's the actual angle that I'm going to use for my vector then? 115, right. Okay, so my vector for my plane has a direction of 115 degrees, and the magnitude, we'll call it vector P for plane. The magnitude of the vector then is given by its speed, because that's how we're using the vector this time. So that's 250. Okay, so let's build this vector then. If it's got a magnitude of 250 and an angle of 115, how do I do that? Bless you. We'll take a look at your notes from yesterday. If I know a magnitude and a direction, how do I do it? Yep.
You find the cosine of the direction and multiply it by the magnitude for x.
Okay, so 250 cosine of 115 would get you the x. And how do I find the y? Same thing but sine, right? 250 sine of 115. All right, take out your calculators. Make sure they're in degrees. Let's get the coordinates for this thing then. When we're done, the coordinates should put us in the second quadrant, right? So we can check our positive and negative stuff there. But this should put us squarely in the second quadrant based on the way our little picture is drawn there. All right, you can double check it, but here's what I got. All right, we all end up with the same thing there. Negative 105.65 and 226.58. So what that means is the plane, you think of this as the vector of the plane heading up right here. All right, its x component is negative 105. Its y component is positive 226. Does that seem reasonable? Yeah. Yep.
Why aren't you adding 180
I don't need to add 180 unless I'm doing an inverse tangent, and it's in the second quadrant. That's the only time you do that is if you're going the other direction with it. If you know the components and you're trying to work backwards to get the angle. This direction, the angle always works no matter what. So we're good. All right, so let's do the same thing for the wind. It's pretty much the same process. The compass rose for the wind, if we can draw this out real quick here. Now we've got 10 degrees south of west. So what quadrant does that put us in if we're going south of west? Third quadrant. So right here. And then this is 10 degrees. All right, starting at west, south of it, 10 degrees. Okay, so down 10 degrees from there. But what's the actual angle we're going to use? 190, right. So for this one, we got 190 as our angle. And what is the magnitude? 40. Okay, so repeat the process. Give me a vector for the wind. All right, so here's what I got. Negative 39.39 and negative 6.95. Again, take a look at where this vector is supposed to be. Does that seem reasonable? Okay. Yep, third quadrant, right? And the numbers on this one are quite a bit smaller than the one we had for the plane. Does that make sense? Yeah, the wind has much smaller components to it, right? It's not as much of a push, not as much velocity to it, so both the components should be a little bit smaller then. So that's reasonable. Yep, that one should work. And the fact that the x is bigger than the y, too, this is only 10 degrees, right? So it's got more x to it than it does y, so that makes sense, too. So, all right. So if we want to figure out the resultant speed and direction of the plane, I got to add these two vectors together and see what I have. Okay? So we add them component-wise. So P plus W. So to get the x component, negative 105.65 plus negative 39.39. And so I've got negative 145.05. So let's think about that for just a second. Okay? My new x component is negative 145.04. Both of these added together. So once I'm done, the plane is going to be moving faster in the west direction. Do you guys catch that? This is a negative x, right? Which means west. Take a look at these two vectors. Does that make sense? That they're kind of working together to push it faster in the westerly direction, right? Because they both have components that move it in the west direction. Now, what about the whole north-south, the y part of it? See how they're kind of working against each other now? The plane has a lot of north to it. The wind has a little bit of south to it, so it's going to take something away from that north component of the other one, okay? So that's why these have opposite signs, right? 226, but negative 6. So they're going to kind of cancel out a little bit, not a lot, because the plane's overpowering the wind quite a bit in that direction. But that's why you got to subtract it away there. So 226.58 minus 6.95. So it's 219.63. So the plane used to have 226 in the northerly direction, and now it's only got 219 in that direction. Okay. I haven't actually answered the question yet, though. The question said, what is the magnitude and direction, essentially, of the plane once it's done? Okay. So I got to take this new vector then. I got to find its magnitude and its direction, right? So think about how we did that. I'm going to go to the next page here because I'm running out of room. But that's what we want to do. So we had negative 145.04. And the y was 219.63. All right, so how do I do that? Magnitude and direction. Okay, so the inverse tangent of y over x. Good, because I'm in what quadrant here? Second quadrant, yeah. So we're going to be off by 180 here. But let's try this once first, just to see what the calculator gives us. 219.63 divided by negative 145.04. All right, so the calculator is telling us negative 56.56 degrees, which we know is wrong because that would put us in what quadrant? Not the second, the fourth, right? So add 180 to that answer. So the new direction of the plane is actually about 123 degrees, 123.44. Okay, and yes?
Wait, I forgot what quadrants do you add 180 to?
Second and third. Yeah. And you can check that out and just ask yourself, because you don't have to memorize that necessarily. You could just ask yourself, is this angle in the correct quadrant? Because I know I'm supposed to be in the second. Is negative 56 in the second? Nope. Okay, it's wrong, so add 180. And then it's right. So, all right, yeah, question?
Do you want it written as 123, or do you want it written as 33.44 degrees west and north? Do you want
Oh.
to negate it, or do you want it just as that?
I'm okay with this. If you want to convert it, I will not stop you. But, yeah, it's good either way. Okay, so magnitude. So let's figure out how fast is the plane actually moving now that the wind has pushed it around some. So how do we find the magnitude of this thing? Yeah. Mm-hmm. Good old Pythagorean theorem here. All right, so let's see what we get there. Square root of negative 145.04 squared plus 219.63 squared. That's about 0.2. All right, and this was miles per hour we said, right? All right, so after the wind has pushed it around, the plane is now traveling at 123.44 degrees, and it now has a speed in that direction of 263.2 miles per hour. Okay, so did our plane speed up or slow down because of the wind? Yeah, it got off course a little bit, but it is going faster. Yeah. So it's slightly off. Our original direction of the plane, remember, was 115 degrees, and now it's been pushed over to 123. Started going at 250 miles per hour, and it's been upped just slightly to 263. Okay, so that's just one example of how you can use vectors, like addition of vectors, that sort of thing, to arrive at a conclusion. This whole gust of wind plane is kind of like a classic one they like to use a lot because it works pretty well. You could have like a boat on the water, and then like a wave comes with a certain velocity in a certain direction and pushes the boat around while it's trying to move. It's the same concept, that sort of thing. Or other ones where you have like, there's some kind of an object you're trying to pull, and then someone comes over to the side of it and gives it a shove in a certain direction with a certain amount of force. That too. I could do one of those if you wanted. Do you want to do a force one or not?
No.
Okay, make sure you read the section then, please. Okay, if I'm going to skip that, then you need to make sure you read the section so you can see that done too. I think would be good. Okay, then I'm gonna be done. Well.